Yes, my name is Ben. Some of you know me. I work at Intel. I'm a principal engineer. I work with Michael and Luke on the power management firmware. And we are very excited about senders and receivers. Now, this talk has a sort of alternative title, which is how to draw the rest of the owl. Thank you to Hannah for this. Yeah, because what you're going to see is the two circles this morning, and maybe some of the feathers. Please assume that all the code you see has all of the bells and whistles. Don't, I know there are people here who are compilers in their heads. Also, I'd like to forestall a question. Please don't ask about compile times, because the answer is unoptimized at the moment. And also the answer is good enough to ship. I'm completely confident in that. But I don't have a good answer as regarding compile times if you wanted to take it for your particular code base at the moment. P2300 is the paper, is the sort of overall paper that covers senders and receivers. There are a few other papers that add on to it. This talk doesn't match all of that, but as it says, it is an implementation in spirit. So please do ask questions as we go. So yes, there's a lot in this talk. Something that sort of looks like an owl. We're going to talk about, first of all, a little bit about how embedded development differs from desktop or server development. And then we're going to get into some basic composition and execution. We're going to look at a few schedulers. We're going to look at some sender adapters. We're going to look at the source code of some senders and sender adapters. Then we're going to look at errors and cancellation. That's a really important feature. And allocation, which you might think is an important feature, particularly in the embedded space. And then I'll have some closing thoughts. Now, you've seen, I think, most of you, Michael's talk. In addition, you might have seen several talks about senders and receivers. Most of them talk about how to use senders, and Michael's talk was great on that. So we're going to go into some implementation in the grand tradition of let's implement something to understand it. OK, so how does embedded development differ from normal development? Maybe you think you know what it means. Maybe you do know what it means. So what does embedded development mean? Throw out some things. What are some hallmarks of embedded development, you think?
No operating system.
No operating system?
Constrained resources.
Constrained resources.
No lights.
No malloc. I didn't hear you, James.
Blinking lights.
Blinking lights from Michael's talk. Yeah,
No UI.
yeah. No UI, naturally.
Maybe no position-independent code?
No position-independent code, yeah. Yeah, all of those things I think are fair. To a lot of people, the immediate sort of constraints are no runtime allocation, no exceptions, limited amount of STL, okay? And I came fairly fresh into embedded a couple of years ago, and this is what I noticed. But in the end, once you get used to these things, they aren't too difficult to deal with. The main thing we're trying to achieve is abstraction in spite of these limitations, right? And in some ways, these are symptoms, I think, not causes of differences. One of the main differences here, and Michael alluded to this in his talk, is that lifetimes are not the same. Non-embedded development mostly assumes that programs end. You write a program to do something, it does the thing, it ends. Even if you're writing a server, you handle a client for a certain amount of time, the client lifetime ends. Embedded programs pretty much always run forever. As Michael said, hello, Lisa.
How many times does one of your embedded programs run forever?
How many times has one of my embedded programs run forever? My embedded programs haven't run at all yet. I'm new to the industry. But we work on power management software inside the CPU package. That means that, and this is the way I explain it to my family, when you turn your computer off, even if you unplug it from the wall, there's a battery on the motherboard. It's sipping microwatts. There's tiny amounts of power that's still running some of our code. So that when you push your power button, the PC comes back on, right?
Well, it's still maintaining some of our state.
Exactly. Still maintaining some state. Probably not running code. But in some sense, it is running forever. And there are machines with uptimes of years, maybe decades. Potentially it is running forever.
That are running forever. I'll let you know.
Yeah, Luke has code that's been running a long, long time.
Yeah.
And we can argue about how to model lifetimes, and that unending lifetimes are really a special case of bounded lifetimes. But really, lifetimes are kind of a proxy for the existence of a main thread, right? You start a program on a main thread, it does some stuff, and the program ends. You have a main thread. In embedded, now a lot of times we do build with a main thread, but I think the promise of senders and receivers is sort of allowing us to get away from that, because there's nothing really special about the main thread. If everything you have is sort of driven by hardware interrupts, event-driven, you do not necessarily have to have a main thread. If nothing's happening in the real world, there's literally nothing to do. So you just go to sleep and save power. You don't yield, you don't get preempted. There's none of that going on, because it's not, the context is not an OS. You literally return from an interrupt handler and you're done. And then when something else happens in the real world, the hardware wakes you back up with an entirely new call stack.
I mean, a lot of UI application programs think this way too. You start everything going, and then you sort of like let the main thread handle events that occur, button clicks and other things. So it's
right. So it's very natural and common to think of the main thread as the catch-all, right? But the way I think about it is like, why do you need that? You can build a sort of slop queue on your main thread for like the lowest priority tasks, but the hardware would handle that for you anyway. Like, you've got n priority interrupts, the lowest one could do that work for you, right? You're just adding an n+1 priority level. And anytime you introduce a queue that can sort of take multiple priorities or slop, you're introducing the possibility of priority inversion. So, I think the promise here is that senders and receivers allows us to efficiently let the hardware wake us up and only use that model. Okay, so in an interrupt-driven program, your job is to get woken up, do what you need to do as efficiently as possible, and go back to sleep. Race to sleep is the key to saving power. Sometimes you do a little bit of work. Sometimes you reschedule something on a different priority. But in this model, there's nothing really. If your work is properly prioritized, why shouldn't you do it in the interrupt handler, is my thought. The hardware will take care of the prioritization. So the other big difference between non-embedded and embedded is that mostly non-embedded programs are all about computation. The program calculates something useful. That's why we write the program. We crunch some numbers. Embedded programs, all programs do two things: mathematics and I/O. Most programs are just, you run lots of algorithms, and the last algorithm you run is the one that allows you to get it in a human-readable format, the data. But embedded programs are almost all about I/O. These are microcontrollers for a reason. Programs that do no calculation at all on desktop are rare. Like, you can enumerate them pretty much. They're called things like cat and yes and pipe to dev null, right? So in embedded, we have a situation like this. The computational hardware power is fairly tiny, but the I/O power is huge by comparison. And that's a fundamental difference. So in senders and receivers land, a lot of work that's been done has been done in the realm of efficient use of large hardware, heterogeneous resources, and we're coming at this from the other angle. Like, can we make sense of composing concurrency? And I think that the last thing I'll say about the difference here is, we tell people mostly the same kind of performance things. We say things like memory locality, caching, branch prediction. Those are all important when you're programming a desktop processor. Microcontrollers tend to be more varied. There might be cache, there might not be. It might be small, it might be only one level. There might be branch prediction, there might not be. There might be different sorts of memory with different latency characteristics. The CPU itself might have differing ability to actually process instructions. And the pipeline might be like 2 stages or 40 stages, or maybe more. So this is cppreference.com page, and this shows what freestanding is. Now, we are not going to be using, freestanding is very restrictive at the moment, overly restrictive, in fact. The embedded toolchain that I use has more than just the minimum, the lowest common denominator freestanding, luckily. So we're able to use regular C++, but basically nothing that throws or dynamically allocates. This means we can use things like array, tuple, optional, even variant, string view. These are all fine as long as you don't use the functions that can throw exceptions. Algorithms, numerics, algorithm and numeric headers, they're fine. And atomics are also fine. I don't know if most embedded controllers have atomics, but certainly many do. And in fact, it's kind of like sometimes programming in the 80s, where the memory model allows you to effectively treat things as atomic sometimes anyway. But none of the other thread standardization or standard things, like no mutexes, condition variables, barriers, latches, none of that. Okay, so what execution context do we have typically? The goal is to hook into these execution contexts so we can schedule work that happens when the hardware wakes up and in between times go to sleep. So typically we have a bunch of prioritized interrupts, right? Maybe 16 of them, different priority levels. At least one, but probably more timer interrupts and some other arbitrary I/O interrupts. These are all execution contexts. Now, I've heard some scary things about interrupts, and coming into embedded, I still ask the question to Michael and Luke, like, why do people think interrupts are so scary? It's because they introduce a certain amount of non-determinism. That doesn't mean that we can't still reason about them, A microcontroller may or may not have atomic operations, but all of them pretty much have a way to turn off interrupts. And in the limit, that might be what you have to do to achieve synchronized work. Interrupts, and while it's true to say that interrupt signals can happen between clock cycles, which is a very scary idea, I don't know, there's no way that the CPU could actually respond to it except on a clock cycle boundary. So that's okay. They may happen in the middle of instructions, but whatever the CPU does to service the interrupt, and Michael talked about this, the CPU will save some state that's happening right now, will maybe restart the current instruction when it comes back. We can model about that. The CPU has to, in the end, present a consistent model of computation that we can reason about, and we should still expect that atomics work, and the C++ memory model still works. So yes, that's kind of the basis here. Richard?
But that's the assumption we have with everything. Like when we think about
Exactly.
Yeah.
I only have this slide because I've heard some scary things about interrupts, and people think that interrupts are somehow magical, but they're not magical, they're reasonable. Okay. So the kind of problems that embedded has, and I mentioned this, a lot of the work I think has so far concentrated on how to program heterogeneous hardware, graphics cards, to solve large computational problems. It's sort of miraculous that for 50 years or more, most of us were programming in the single-threaded abstraction model, when hardware has always been fundamentally parallel. Like when you get down to voltages on wires, it's an abstraction. Single-threaded is an abstraction on top of that. And so race conditions arise from hardware. And I'm deliberately saying race condition rather than the C++ term data race, because you can still have single core, if you have a single core processor, you can't have a data race in the sense of it two threads concurrently accessing memory, but you can still have race conditions because of things that the hardware does. Okay, so the promise of senders and receivers here then is a declarative style that makes code reasonable. So we saw that in Michael's talk. Let's get the code together so we can reason about it and not have it distributed across multiple places. And this abstraction that enables us to treat hardware interrupts as execution context, and in between doing any work, go back to sleep. All right, let's talk about the basics. Let's talk about schedulers first. Now this is, I'm starting off easy here. There's not much on this slide. It doesn't say much yet, but this is what a scheduler does. It has a schedule function, and that schedule function returns a sender. And the inline scheduler is like the simplest one you can imagine. It acts as if, when you give this work to do, it will do it as if by a function call, regular function call. So here's a couple more that I alluded to. The priority scheduler and the time scheduler. Now these represent those interrupts going off. So when there's a typo on the slide there, that should say schedule on line 7, not scheduler. When I call schedule on these, I will get a sender. That sender represents work that will happen, that will start to happen when those interrupts fire, either when the priority interrupt fires or when the timer interrupt fires. And so here's your blinky light. Who said blinky light? James. Here's hello world, if you like, in senders, in embedded senders. Schedule on the timer scheduler, 1 second, and that's going to go off in 1 second's time, presumably. Then turn the LED on, then schedule again for 1 second, then turn off, and keep going, repeat that. This is just a declaration. This doesn't do any work yet. This is just describing what we want to happen. This is in pipe syntax. It's entirely equivalent to this. So this pipe syntax is very much inline, nice to read. But this is an implementation talk. So what's actually happening is that each sender in that pipe is wrapping up the previous sender. And you can see this from a bit, this is much harder to read than this, but this is actually what's happening in sense of senders wrapping each other. So on the inside, we have the first scheduler, line 6. Then we have turning the LED on, wraps that. Then we continue on the timer scheduler again, line 8. Then we wrap that. Finally, we wrap the whole thing in a repeat. So you can see the nesting. And this is what that nesting looks like in a diagram. So the scheduler gives us the sender. That's on the inside. And then all those other things are sender adapters. And every time we pipe something, we get an extra wrapper around. So in the end, we get this type, which is the fully wrapped sender onion, if you like, this nested structure. Now, when we execute them, it looks like this. And we say start detached or something. This is a sender consumer algorithm. And under the hood, what it's doing is, in Michael's talk, he said, you didn't really mention receivers. That's, in user code, you don't see receivers. Receivers are the glue inside this onion that we use to connect the senders together when we start the work. So when we say start detached, what happens under the hood is we connect that onion, that outside layer, and we start it. And that connect call, in turn, connects all the way down. So we get a structure that mirrors all these wrapped senders. When we call connect on the outside, it calls connect on the sender that it wrapped, and so on until we get to the inside. And each connect call involves one of these kind of internal receivers, right? And when the sender and receiver connect, that's an operation state, and they wrap each other just like the senders did. Yes, Richard.
Just to check though, are the colors significant here? Like I call connect on the outside one, does it become the most inside one, or does it maintain the structure?
The colors reflect, well, so if you're talking about this arrow going through to the inside here, is that what you mean?
Yeah, sort of.
So this reflects that, connect on the out, so they will happen from outside in, but this part of the arrow, if you like, that's drilling in, that represents that sort of recursive connection. So it's not that you're not directly calling into the middle one. The outside one doesn't become the inside one, but it does connect all the way down inside, right? So we get an operation state onion, which mirrors the structure of the sender adapters. Yeah.
So on your previous slide, where did the receiver come from?
We'll get to that. These are typically internal. So for each sender adapter, it might have its own receiver type that it uses to do whatever it does. But we'll get much more of that. Okay, so we declare the senders. We get this wrapped state. We connect the senders, or we use sender consumer, and it calls connect on the inside. And we get this operation state, which is mirroring the structure. Then we start it. And once again, start, drills in from the inside. And, the one on the inside is running first. And then that completes. Next one starts running. That completes. Next one starts running, completes. Last one completes. And now the whole thing is complete. So until the last layer is done, all of the stuff on the inside is still alive, right? This is what structured concurrency gives us. The lifetimes here are all bound up in this thing. This is a real object, and it has a lifetime.
Is it like stack traces or something?
You can think of it a bit like stack traces, right? But instead of function calls, these are asynchronous function calls. That's we've stepped into asynchronous land. Yeah.
In your particular example, the outermost operation never completes, right? Because it's a repeat.
That's right. Yes. So it could complete if there was an error.
Oh, okay.
But yes, if everything's going well, it runs forever. Yeah. So the inner one here would be the schedule for 1 second, and then we have the turn LED on, and then we have schedule for another second, and then we have turn LED off, and that would be one time around the loop.
And typically, once a sender gets moved into the onion, is it common to have a way to access it? Like, are there like dot-based member functions or? No.
There are. So we'll see how the outside can control things like cancellation, but there's no way to look inside the onion and look at the state. Like that's not something that happens. Okay, so we start with a sender factory. That is a function that returns a sender. Then we chain on as many adapters as we need. These are functions that take a sender and return a sender. Sometimes they have other stuff that they take, like this takes a scheduler and a sender, right? And we end with the sender consumer. And that is what kicks off the work. If we took this off, none of this would do any work at all. It's just a declaration. Okay, so that's the basics. So we have schedulers. These represent the execution context. And when we call schedule, they produce senders. We have senders that we compose with adapters. And then the receivers are the behind the scenes thing. Like for each sender adapter will have its own brand of receiver, mostly. And then the operation states. Now, I want to say in general, those operation states are non-movable, right? Everything else is movable and pretty lightweight. But the operation states, they are the work. They are the lifetime of the work. And in general, they're non-movable because they might contain synchronization primitives like atomics, like on desktops, it would be mutexes, maybe things like that. All right, let's look at a few schedulers. By the way, if you want to spruce up your office, hundreds of googly eyes for a few dollars. It's a good tip. So let's look at the timer scheduler. So we know that when we call schedule, it returns a sender. And that sender's not going to be that sender's pretty much just going to capture the duration here. So what does the sender do when we connect it? And we're going to see some patterns play out here that will play out repeatedly. Now, my implementation uses tag invoke. I'm aware that's been taken out of the paper. This is a call. You think of this as a call to connect a sender and a receiver, right? And it will return an operation state. So let's take a look at this function in a little more detail. The template head, this is an implementer's choice. This is a convenient way of handling value categories, or at least there may be other ways to do it. This is the way I started out doing it, so this is the code I have today. So this function is going to take a time sender, right, with any kind of CV qualification. This is just saying that. and it's going to take a receiver. The receiver is a lightweight concept, pretty much just says it's movable and it has an environment, and there's a couple other things. We'll talk about environments later. Notice this template head is not yet checking any kind of compatibility between the sender and the receiver, right? We don't know that the receiver can handle what the sender sends yet. Okay, so yes, you're going to see tag invoke. I might change this, but this is the way it currently is. I began the implementation when P2300 was based around tag invoke, and it's not now. I'm not really going to explain tag invoke in this talk, but basically whenever you see code of this form, it's really just the same as you're invoking the member function called tag on the object with some arguments, all right? And the tag is going to be things like connect, start, set value, set error, set stopped for receivers, things like that. Everyone cool with that? Okay. This function, the first thing it does is does that check, right? Can that sender, or can that receiver receive things that that sender sends? And we'll talk about sender signatures in a bit. I'm saying that a lot, aren't I? We'll get to that later. We'll get to that later. Basically, senders advertise what they can send, what they might send, everything they might send. And the receivers have set value, set error, set stopped calls for the value channel, the error channel, and the cancellation channel. And those two things have to match up, right? And that's what this is saying. Richard?
Curious why you chose to do it as a constant value, not like it requires.
Yeah, good idea. I did have it as a requirement. But I found that it's easier for users to do this. Most of the time, so it's a common error when you try and connect a sender and receiver. And remember, that's inside the start detached call or something like that. You really do want those things to, like, you haven't really made a mistake in the intent, right? What you've made a mistake in is like something doesn't match up somewhere, but you want to call this function on this sender, right? The sender part is really fixed. You've made the sender, you want to call this function. The fact that it doesn't match up isn't a problem of the overload set. You will end up calling this when you've fixed everything up, but in here is perhaps an easier diagnostic. Kirk, I'd love to hear what you have to say.
Where, your requires is really for spinning normally, and so you don't really, in these cases where you're checking connect, you don't really want the function to disappear from the overload set, which is what spinning would do if you had a trait in a requires. So what I've started doing is building assert traits that static assert on false internally. And so then I can list my spinning traits in the requires first and follow them with my assert traits. And I get much earlier compile errors that are very descriptive, and I never spin A out, check connect, or these types of errors.
Good. So I want to call that function. I just need to finding out why.
That's it. We don't want this function to get removed from the overload set, because in the end, the user does want to call this function, like Kirk said. Okay, so the function itself, the body, is a one-liner. All we're doing is returning the operation state that will result from connecting the sender and the receiver. And in many of these cases, like you see, the operation state, what goes into the operation state is usually the receiver and something the sender had, right? In this case, the duration, because this is a time sender. So what does the operation state look like? Well, we're seeing some embedded stuff creep in, but the senders and receivers part is right here, line 7. This is the start. We're going to call start on the operation state. What's it going to do? It's going to hook into the task handling machinery, right? This run after call on line 8 is us telling the hardware to schedule the interrupt through a task manager, a timer manager, right? And so this operation state for the timer is a timer task, right? You can see that line 3. You can see, like I said before, they almost always have receivers in them, and the receivers are often empty, so I put no unique address. And some state, line 4, which the sender had, right? So we actually know what we're going to do. It's a timer task. What does a timer task look like? So really, when we have a timer interrupt, we're going to queue something up to run, but we don't have allocation. So usually what that looks like in embedded code, in our code anyway, is intrusive lists, right? And here you can see line 4, a timer task has intrusive list machinery, right? So these tasks are going to be statically allocated. And they're going to have stable addresses, right? Because they're in an intrusive list, so they're not movable. That's okay. The timer manager is the thing that interfaces with the hardware through a HAL, but it basically has these two functions. We're going to ask it to queue up a task after a certain time. So it's going to keep this sorted list, and it's going to tell the hardware to say, set your timer interrupt for the time at the head of the list and enable it. And then when that timer interrupt goes off, it's going to call the interrupt service routine, the ISR, and we're going to execute that first task, and then we're going to queue the next one. We're going to schedule the interrupt for the next one if there is a next one. All right, so that's, all these functions are pretty simple. Here's the operation state again. So yes, so this is the recap. That call to run after ends up calling the run after function here. I've omitted that's just some C++ism. There's some machinery there, but it's not important to senders and receivers. Now, when that ISR runs, when it runs the timer task, it's going to call run line 8 on our operation state. And this is a schedule. This is a sender that we got from the timer scheduler. And when you get a sender from a scheduler, it just represents starting work in that context. So there's no work to do here. There's no computation line 8. All we're going to do is call set value on the immediately downstream receiver, and then that's presumably going to do some more work that got chained off. Okay, so this pattern gets repeated for a lot of things. The scheduler gives us a sender, and then we connect it and get an operation state. When we start that operation state, so up until now, no work happened. Only happens when we start the operation state. That's when we enable the interrupt, and we return. And then the interrupt fires, and then it runs the operation state, and now we're off and running. The downstream sender chain is running in that interrupt context, on that timer interrupt. Happy? Yes, Roy.
So set value being called in the receiver will eventually invoke start on the next one in the chain? Or?
Yes, it depends on the adapter, but yes, basically that's how the execution proceeds. Richard.
So if there's already a timer running, like you have several timers set up, it looked like you're adding. You can have a list of timers and all these various things. So is the timer interrupt enabled when the op is started?
Yes,
For the
through the
and then everything is just attached, or?
So the timer manager has a queue, right?
Yeah.
So if you have multiple, you can, every one of those schedulers represents a different interrupt context, which is a different, execution context fought by the timer interrupt. This manager handles the interaction with the hardware. So it says things like, okay, it looks at the head of the queue and it sees what time is that, and that's when it sets the interrupt to go off at that time. And it knows whenever the interrupt goes off and this function gets called, the ISR, run the thing at the head of the queue. And then if the queue's still got stuff in it, take the head again and schedule that interrupt, right?
Got it. And the run after is doing all the complicated work of figuring out, oh wait, you're first in the line.
Yeah. This is just doing insert at the right place, and yeah. It's not too complicated. You can imagine the code. It's half a dozen lines.
And the timer manager is sort of global, so it has.
Yeah.
Sorry,
Well-
it has run after calls from a lot of different sender chains.
If you only have one timer interrupt in your hardware, yes, it would be one global object. If you have multiple, you could have multiple of these. There's some template machinery we do to inject them and name them with templates. So you can.
This is handling timers from multiple sender chains.
Yes.
Not just
Yes.
not just the one
Absolutely.
sender.
This is handling. Yeah. Let's say you have one timer interrupt. This is a global object that's handling all of them, right? and all of your timer schedulers end up getting into this list, right, when they're started.
It really represents the I/O device, right? So it is a singleton for
Yeah.
every timer that you have in hardware, right?
Right, exactly. Question?
So we build an onion of the work that we want to get done, but nothing's happened yet. And then when we call
Right.
start,
Mm-hmm.
compile time, so it's both runtime and compile time, right? At compile time, the start function internally connects all the layers of the onions together. Is that where that occurs?
The connect is a runtime function. I mean, with a lot of these things, the structure of the types mirrors the structure of the computation.
So,
The start stuff and the connect stuff still happens at runtime, right?
So
The connects
question is-
normally don't have much to do apart from just copy some state into operation states.
my question is, at some point at compile time, we connect the senders using the receivers, and the layers of onions get turned into an operation state, right?
That happens at runtime.
At runtime, okay.
Yeah. Yeah. Okay, the priority scheduler, let's go through that quickly. It looks very similar to what you've just seen. It gives us a sender. When we connect the priority sender, guess what? We're going to do the same kind of things. This time we're going to get a priority operation state. And rather than being a runtime value, like the time, the priority now is known at compile time. And there are ways to do this either way. There might be cases where you want to do the priority at runtime, but this for the moment is for compile time. The operation state we get from the priority sender looks just the same as the timer one, except there's no time. There's a priority instead, line 1. And when we start it, instead of calling run after and interact with the timer manager, it's going to interact with the priority manager. And it's going to queue a task at that priority. And it is a priority task, just like the other one was a timer task, line 2. And the priority task also is an intrusive list type thing. This is statically, this is known at compile time, the storage for this, and therefore it's not movable, and it has a run function. So this is just really the same pattern as we saw with the timer task. And when we call run, they're going to do the same thing, right? Because this is still, we got it from a scheduler. It just represents starting in that context. It's going to start the downstream work. And the priority task manager, again, global object. Instead of handling timers interrupts, it's handling priority interrupts. And it's got, instead of a sorted list of things by time, it's got an array of lists, and each slot in the array is a different priority. So again, just like the timer manager, when we queue a task on the priority manager, it's going to just push it on the back of the appropriate priority queue and enable the interrupt. That interrupt might fire immediately, right? If it's a higher priority than we're currently running in. And then the interrupt's going to call the interrupt service routine line 12, and then that's going to execute all of the tasks at that priority. So this is the same pretty much as the timer stuff.
Okay, so this
Yes.
is it's a way to assign a queue of work to a particular hardware context, right? The ISR represents
Yeah.
whatever sort of, it could be your timer, it could be any sort of interrupt, but when
You
that comes up, it'll have a list of things to do.
Yeah. So this is just showing really how, the abstract idea of senders and receivers, schedulers in particular, can hook into concrete hardware, right? And it's pretty simple. It's not.
And each of those task objects, they just remove themselves from the queues that they belong to on their destructors. RAI stats,
So they don't get destructed because they are static objects, but they do get, when you execute that list of tasks, you do something like resetting the pending flag, right? So they get removed from the list, but they're ready to be
that's part of
reused.
the ISR or part of the
Yeah.
run function.
Yeah. Well, this is gonna have a loop that executes each task. Each task is the run call. Yeah, exactly.
So how does this handle cancellation?
How does this handle cancellation? We'll get to that. I mean, it handles cancellation by removing tasks from that list. But how you drill into that, yeah, we'll cover that. There is one thing to note here. So when you execute a list of priority tasks, you've got two choices. You can execute that list live, right? And the task that you run might queue up tasks, might end up starting tasks at that priority. So you've potentially got an infinite loop. In fact, in test code, it's rather easy to create the infinite loop. Or you can sort of do an exchange of the queues, run the one, and anything that requeues itself, it requeues to the new one. I think Tony has a whole talk about this kind of issue. But the default safe thing to do is exchange the queues and allow the new things to requeue themselves on a new queue. Okay, so there's a question, Jody.
Yes. So each sender in the pipeline can be associated with a different scheduler.
The scheduler gives you a sender that starts the pipeline. Once you have a sender, you're using sender adapters.
Right. Okay. So
Right.
Can if you've got a pipeline, can each one of them have their own schedule, or is the whole entire pipeline
There are sender adapters like continue on that allow you to change which scheduler you're running on.
Right. Okay.
So yes.
Yes. So in that case, how do you handle flow control?
I'm not quite sure what you mean by flow control here.
Well, let's say that you're handling something on another thing, and I know that and so that you've got a queue of things. Well, that you don't want that queue to just keep growing and growing infinitely. You don't have memory for it, so you'll need some type of flow control mechanism.
Well, okay. What you're hinting at, and what a couple of questions have hinted at, but we haven't addressed entirely, and really is beyond the scope of this talk, is that the fundamental problem of programming embedded systems is you have hard limits. So your whole system has to be programmed in a way that you will not exceed those hard limits, right? Everything is statically allocated. So you will have, you can't have more than 8 things queued up on one priority or whatever it might be, right? This is a property of the system as a whole. This is not necessarily entailed with how senders and receivers work. Luke.
A really important design decision to handle that is the intrusive lists. The intrusive linked
Yes,
lists.
yes.
Because we have an intrusive linked list, we don't have to say ahead of time, oh, this queue for the scheduler is only 8 long, right? It's not an array, it's an intrusive linked list. And we had to already statically allocate all of the nodes for that, right? So if we can compile, then by definition, we can queue up everything and we'll work.
So
Yeah,
they're not
yeah.
connected until the runtime. They're just
Exactly.
there in memory, and then so you can count how many objects there are. You can see it just in the stats and go,
There-
hey, this will fit on this microcontroller.
I mean, it'll fit because it'll compile and link.
Well, I mean,
Yeah.
the memory image will fit in the RAM of the whatever
Yeah.
Yeah.
ROM or whatever.
Now, you do have to deal with reentrancy in the same code bar affecting the same object when it's busy. So you get that problem. But these are intrinsic to sort of embed development systems. They're not necessarily problems of senders and receivers. Okay, let's look at some sender adapters. So let's actually do some useful work, right? We've got something running in an interrupt context. Now let's actually do something. Okay, so Roy, I think, asked about receivers. This is a primer for receivers. So this is the simplest receiver you could possibly have. It does nothing. It's the universal receiver. So whatever a sender sends, it will take and just drop, right? And the channel tag there, you can see, so this is, we're either calling set value, set error, or set stopped on the receiver with any arguments, and it does nothing. This is an extremely useful receiver for testing. Now, I mentioned earlier, senders advertise what they send, and they do that at compile time. And one way they do that would be exposing a completion signature's type. Now, these completion signatures may depend on which receiver they're connected to. So there's a more involved way. But the idea is true here. No, a simple sender might do something like this. And this is saying that, when this sender gets connected and started, 4 things might happen. It might complete with just an int, or it might complete successfully with an int and a float, right? Or it might complete on the error channel with an int, or it might allow cancellation and complete with stopped, right?
Oh, so this could be a way, like, I'm jumping ahead probably, but like if I have an ISR, like some interrupt handler, and there's from a number of different peripheries, say a UART channel or an ISR,
Yeah.
you could the ISR could say, okay, I'm going to complete, and I'm going to give you the address of the peripheral that's having the problem, or maybe even the opcode that I received from it. So that could be sent down further to the other channels, the other sender adapters.
Right, exactly, yes. Yeah, you typically send something and the next adapter in the chain would do something else. It's like transforming a range or something. It's the same idea, except it's asynchronous. Okay, but importantly, a sender might complete on the same channel with more than one completion, right? Yes?
Are those completion signatures like slots that you can connect to different senders?
Completion signatures represent like how a sender may complete, what a sender may produce, right? So the receiver, Kirk's got his hand up. I'm going to let Kirk answer.
Think of completion signatures like decal type for the return of a regular function. This is decal type for the return of an async function.
Yes, perfectly. Thank you, Kirk.
It can be one of them.
These-
So the receiver needs to handle all of them, just to make sure.
Yes. These are functions that might get called asynchronously. Yeah. Yeah, I think I've said this. Whenever you see a pipe, it's syntactic sugar for the nesting thing. I'm using pipes to help us all out. So we've seen then in action already. Then is probably the simplest sender adapter. And it's just like transform, right? We'd call it transform on ranges. It takes a function. That function, you pass that function whatever is sent from the previous sender. In this case, the schedule sender sends nothing, so the function takes nothing. Sender adapter functions, top-level functions, tend to be quite boring. They're just one-liners. So you can sort of guess what then does. It takes a sender and a function, and it wraps them up in its own, this is the top-level then function. But what we're going to do is wrap up this stuff in a sender inside like the associated namespace, right? Sorry, I didn't mean to, associated namespace is a C++ term. I meant the namespace associated with this then function. What does the then sender do? Here's the connect call for the then sender. We can see that. And it's going to, actually then is simple enough, at least in my implementation, it doesn't need its own operation state because it's just calling a function, right? There's no asynchronous machinery there. There's nothing fancy to do. It's just going to, whatever the sender upstream sends, then is going to transform it with the function and call set value on the downstream receiver. And so you see that here. It's going to use its own receiver. So this is very characteristic. Every kind of adapter, usually pretty much all, I think, have their own receivers. And that's what they use to kind of get into the chain. And so the upstream sender is going to send this receiver something, right? And then when this receiver receives something, when the upstream sender sends it, we're going to call the function that we have on those arguments. Whatever comes back, we're going to send it downstream to the downstream receiver. Cool? Good? Like I say, it's just like transform. And then then doesn't have any concurrency orchestration machinery, which is why it doesn't need an operation state. It really is this simple. So we're just interposing this receiver between the upstream sender and the downstream. David.
So the then adapter can only pass one value on to the next.
Interesting you should ask
because
that.
It has a function, because it
Yeah, because functions can only return one
return
thing.
value.
It's almost like I planted you in the audience here. So yeah, if you wanted to return multiple things, you would have to tuple them up, right? And this is how it's proposed currently in the paper. In my implementation, I recognize this asymmetry, right? So my version of then, and it's some meta programming, but I think for this crowd, you can kind of intuit how it might work. That's a gasp from the audience. Okay, so yes, you can stack up as many functions here as you want, and whatever gets sent, just as you saw that in Michael's talk, whatever gets sent just gets the arguments distributed among the functions as is possible. And so then now sends two things on the set value channel, right? It sends an A and it sends a B, and this function returns a void, so that's filtered out, right?
It swallows the argument.
Yeah.
And if you've seen my talk,
And yeah, Gashpa has a mathematically sound, like theoretically based generalization of this.
and we do that.
Right. So yeah, this is just a bit more ergonomic. You know, users don't have to pack and unpack tuples. So I recognize this as being a potentially good thing. So this is what my then looks like.
We could just have one lambda with all three
You could have one lambda with all three arguments. You could have any amount of lambdas with no arguments.
Okay.
You know that, yeah. Okay, I do need to speed up, so I will keep going. So upon error and upon stopped are the same as then, except they work on the other channels. So they just transform the other channels, right? So if something sends an error, upon error handles it, and it still completes on the value channel, right? You've handled the error in upon error. Upon error is going to send this on send nothing in fact, but send on the value channel, right? And the same thing with upon stopped. Let's look at let value. Let value is easy for me to tell you in a one liner what it does. It's just like then, but it returns a sender. The function itself returns a sender. Fair warning, it's neither as mechanically simple nor so close in meaning as the one-line explanation suggests. So the first thing is, what should let value's function return? In a way, the point of this is to return different things, but obviously a function can't return different types of senders. This function needs to return one type, right? That's how functions work. So we do need some kind of type erased interface or variant. In my implementation, this is variant sender, and you make it with a function like this that basically has a condition and a couple of consequent and alternative, right? But this, I think something very similar to this was in Steve Downey's talk from last year. So that's one problem, but fairly easily worked around. So let value, what does let value do? Well, here's the driver function, and it looks just the same as pretty much every driver function you're going to see. It just makes a sender, but it's a let value flavored sender, and it's wrapping up the stuff we give it. So what does let value have to do when we connect it? Or when it returns an operation state, and what does that operation state do when we start it? It's gonna have an internal receiver, just like then did, and it's gonna connect the upstream sender to that internal receiver. I'm reverse mute, so I should be doing this. It's gonna connect that upstream sender to its internal receiver and start that. When that finishes, and set value is called on that internal receiver, calls the function just like then did, but now it gets a new sender back, right? So then it takes that sender and connects it to the downstream receiver and starts that, right? So it happens kind of in two parts. And there's some involved stuff we have to do to complete to do some metaprogramming to figure out the completions, right? Because that first sender might not complete on the value channel. It might error, it might be canceled. It might complete several ways on the value channel. We need to basically call our function in all of the ways we could, or figure out what it will return, right, in each of those ways. And that's going to be our sender, our sender that goes downstream, right? So there's some metaprogramming. So this basically says, give me the value completions, it partitions into value completions and other, because we're going to be transforming the value completions. Get all the things that we could out of that function with each value completion, like the types of things returned might depend on that. Then we've got all those senders, and they're going to complete in potentially all different ways. So we've got these dependent completions, and then we put those together with the ones we don't bother to change, the error and stuff and that. Okay, that's a bit of a wall of code. But you get the idea of what the industrial implementation has to do. But here's the connect call, right? So we're going to squirrel away the receiver and the function in the operation state. That operation state, when we start it, here's the receiver first. That receiver from the upstream sender is going to call the function here, just like then did. There's the function call on line 8. And it's going to tell the operation state to complete the first one, right? The first half of the thing is done. The operation state is where tricky stuff lives. It's where, in general, right? The operation state does stuff. And here's what the operation state looks like. So we have that. So the first receiver is what we saw, right? It's going to keep a pointer to this operation state. And that's fine. This operation state is not movable. It's stable. This is all metaprogramming. So our real operation state is going to be like the union of, for that second part, the sender we get back from calling the function, right? Connecting that to the downstream receiver is going to give us an operation state. And there might be several ways for it to give us back a sender, and we're going to have some dependent operation states, right? So we're going to have a variant or a union of all these operation states for the second part of the computation here. When we construct this operation state, it's going to do the thing of connecting the upstream sender to our interposing receiver, the first receiver for the first part, right? And here we see another typical pattern, right? Because operation states in general are not movable, we need to do the eliding thing. Who was it who showed this? Was it Robert? I think it was Robert's talk the other day. Yeah. This with result of is a thing that captures the function you give it, and it has an implicit conversion. Oh, I have it on the next slide. It has an implicit conversion to the result of calling the function, right? We can't call the function eagerly, because that would mean then we get an object that we have to move, and the operation state is not movable, right? So this is a little thing. I think this might be proposed for standardization. I'm not sure what it's called. Robert did mention the standardization paper.
I don't think it's been in the mailing yet.
Okay. But we use this, as you can imagine, operation states aren't movable, so this gets used a lot. So when we construct the operation state for let value, we connect the upstream sender to our internal receiver. And we store that operation state in our variant of states. When that first sender completes, this is our interposing receiver's set value calls this function. We're going to figure out, which kind of completion or which kind of sender it gave us, and then we're going to connect that sender to the original downstream receiver and keep that operation state, right? So it's a little bit involved, but it's not too bad. I hope it's just some metaprogramming and some C++ gubbins. But basically, here's what we did. So then was very simple. When the upstream sender completes, it calls that function, and then the downstream receiver gets the result, right? In both cases, for then and let value, we have that. Remember you saw that the operation state diagram with the receivers at each thing? Those are the interposing receivers that each sender adapter kind of uses to do their work. And for let value, it does the appropriate thing, right? It does that thing in two parts. Okay, so as for let value, we also have let error and let stopped. And they are to let value what upon error and upon stopped are to then. So they handle things on the error channel and on the cancellation channel. And otherwise, they just work just the same as let value. And now you might be thinking like, so I said the code was simplified and that implementations get more generic over time. You'd be right in thinking that then, upon error and upon stopped, all actually work in terms of, something that's parameterized over the channel tag, right? And the same way for let value, let error, let stopped. And just like we saw with the upon error and upon stopped, these senders, these senders are handling error and are handling stopped. So when these get run, they'll complete on the value channel, right? Okay. Any questions at this stage? Chris?
Is the let value, I guess, let error and let stop as well, are they like the sender receiver version of...
Are you saying a word that starts with M?
No.
Okay.
Starts with F, but also then goes into map, flat map.
Yeah, flat map is monadic bind, and let value is monadic bind, yes. And then is fmap.
Ah,
right.
Cool. Thank you for translating to ranges.
Right. Okay, given just then and let value, we already have a lot of compositional power. And we can put together some very useful senders. Yes, so these then is fmap and let value is bind, or they're the equivalents.
Or then is transform and let value is and then?
Yes, yeah. If you want to put it that way, sure. Let value, because it's the monadic operation, it's quite often more power than we need. Sometimes, quite often, we need to sequence two senders, and there's no data dependency between them there, right? We just want a temporal dependency. And so there's no runtime choice. So the full machinery of let value is a bit too powerful. So a thing that I have is sequence, which is really just the same as let value, except that there's no dependency between the senders. The second sender here can either be lazily computed or eagerly computed. If it's eager, if you already have a sender, then there's the opportunity to do more stuff at compile time, because with let value you can't cross that boundary because it's a runtime choice. But where you have two senders already that you know the types of at compile time, you have the opportunity to cross that boundary more easily, and you get forward transmission of certain properties. Okay, so that's really the difference there. There's room for perhaps several things in that space. You should talk to Kirk after the talk if you're interested in learning more about that kind of thing. Yeah, so what I just said, the monads are really powerful, and in fact, they're so powerful that quite often we don't need to use all that power. And if we don't use all that power, we get more things at compile time. Like using that power means giving things up. Paradoxically, I know, but it's that runtime choice. Sort of another way to look at this is oftentimes what we want are sender adapters and not senders, right? Michael's been working with this for a few months, and at the beginning he was always asking, I've got two senders, how do I compose them? And until we had sequence, it wasn't easy, because composing just senders to get you want to compose sender adapters. Sender adapters are asynchronous functions, if you like, right? We compose functions, we don't compose values. We compose sender adapters, we don't really compose senders in the same way. If you want to compose senders, they need to be lifted into functions, which is what sequence and let value and things like it do. Okay.
Does it make sense to just overload then?
Does it make sense to overload then? I'm not sure what you're getting at.
Then if it's available, then it's then, and if it's a sender, then it's a sequence.
Oh, I see. You want to overload then so that if it takes a function returning a sender, it turns into let value or sequence?
If it takes a sender itself,
Yeah,
it
just
behaves like sequence.
you're like saying,
That-
do this, then on this sender do this. And
So what
oh,
happens
well,
if you have a sender that's also callable? No.
Y-
Your list of senders.
yeah. That way lies danger, I think, is the general consensus. So let's look at a couple of useful things that we can build given these tools already. Start on is a function that takes a scheduler and a sender, and it runs that sender on that scheduler. It chains that sender onto the result of calling schedule on the sender. That's a one-liner pretty much, right? In the paper originally this was called on, but the names have changed recently. So starting on a sender is easy. What does continue on look like? It's a little more involved because we need to pass data through, but it's not too much more involved. So we're going to run the sender, and then what it sends we're going to pass into a let value function, and inside that let value we're going to return start on the scheduler that we were given.
And could you have used the pipe syntax there, or is that just with
Could I have used pipes? I don't think I could. So start on is inside the function we passed to let value, so I couldn't pipe that.
Yeah.
But I did pipe, line 3 is piped. This used to be called transfer in the paper. Yes?
Should the capture scheduler be a by value here? Are they supposed to be like copyable? Or I thought the scheduler was kind of a thing, right? Instead of some value that the
So most things apart from operation states, at least in the embedded world, are trivially copyable. Schedulers are not a big thing. Like we saw.
like the timer scheduler.
Yeah, we saw the timer scheduler.
It has its own internal state, right? If I copy that, then
The timer scheduler has a duration, right? It's real lightweight.
It's the timer manager.
Yeah. The schedulers tend to be pretty lightweight. So, we could move this in. Sure, we could forward this in, but it's slideware. Yeah, Gashpa.
Same as an allocator is not the memory resource, it's a handle to a memory resource. A scheduler is a handle to the underlying abstract IO,
It's a handle.
It is, right? It can have some configuration, but it's usually a really, really small thing.
Right. Okay.
All right.
It's a handle.
I think everyone's okay with this, so I'm going to continue. I need to continue. There's two more really important adapters, when all and when any. They are more complicated under the hood, no doubt. I'm not going to show you the code, but I'm going to go through and you can kind of intuit what needs to happen, right? When all takes n senders. So internally, it's going to connect them to n of those internal interposing receivers, producing n operation states. It's going to start them all. It's going to have some machinery to catch what they all send, and it's going to have like an atomic counter that counts down till they're all done. And if any of them complete with error, it's going to cancel the ones that are still running. But it's going to finish when they all finish in some way, and then it's going to send on whatever it needs to send on. And all of the machinery inside, the boilerplate looks very similar to what you've seen. We've got interposing receivers. We've got to take care of those operation states. We're just tracking more things. There are some reasonable limitations we can put on when all. One of them that the paper has is that all the senders you pass to it must have just one way of completing on set value. If that's not true, you would get a combinatorial explosion of the possibilities that when all could send, because you'd get the Cartesian product of everything that every way they could complete. It's a good idea if they all have the same set error completion. Usually that's something you want to do. It's not a pipeable transformer because it's not a binary function, right? Because you're taking n things. And I don't quite know what the paper says about allowing when all with 0 arguments or 1. But if you have it with 0 arguments, at any rate, it would complete immediately. It's the unit for the monoid, it's for the and monoid, if you like. When all could be called then all in some way because it is the applicative functor characteristic function. I'm going to skip over that. You can see my talk last year for more on that. And talk about when any. So when any in user code is, well, when any is a very general function that could be parameterized a few ways. The basic operation is that it's going to complete with the first thing that completes, and cancel the rest, and just so it's when any is what it sounds like. But we have some choice over what we want to complete with. Do we want, and how we want to do that? Like the first successful one, the first success or error, right? And there are a couple of things we can do with a binary version of when any that are really useful building blocks, you know, and we would call them things like error when and stop when. So this is how you might implement a timeout, right? You would simply schedule using the timer scheduler. That goes off at some time in the future. That's a sender that will complete in 1 second or whatever. And when it completes, you might send a timeout error on the value channel, for example. So if that beats the sender S, then that's what a timeout means, right? Otherwise, the sender S is completed in time, and the when any would complete the way S completes. Cancellation might also be a GUI operation, right? Something's going and there's a cancel button to click. That's the second one. And again, we're effectively racing two senders, right? You're racing the calculation with the user clicking cancel. So yeah, there's a few design decisions that are fairly similar to when all. Should all the senders we pass to when any have the same error completion? Probably. It's not like when any, like when all. When any is not, in the general case, pipeable because it's an n-ary function. But as we just saw, there are very useful binary versions that are pipeable. And we should find suitable names for the variations. When any is not, the paper makes reference to some things which are sort of implemented in terms of when any, but when any itself is not, as far as I'm aware, proposed for standardization yet. Is that right, Kirk? Yeah, Kirk's nodding. If you call when any with 0 arguments, again, it's the unit for the OR monoid. It never completes. In other words, whatever you race it with always beats it, right? Is that dangerous or is that useful? You know, it might be dangerous in user code, but useful in generic code. It's one of these things. Important thing to note here. The structure concurrency means that lifetime is controlled in that nest of operation states. Cancellation is cooperative. When any and when all complete as a whole when all of their things complete, right? In the case of when any, they still have to complete. They just might be cancelled because the first one won, right? But the overall sender still completes in a way that ensures that the lifetime of all of the sub-objects is covered. David.
How do when all and when any signal cancellation?
How do they signal cancellation? Yeah, so they deal with some concurrency orchestration, right? So they heed cancellation requests, if you like, in a way that then doesn't. We'll see that. Okay. I need to get to it. All right. People might find this a disturbing picture. It happened to me. Let's take a look at errors and cancellations. So we've already seen some handling of errors, right? In general, if adapters don't handle the particular channel, they will pass it through. And so we get this nice compositional way of handling errors like this. So let's talk about cancellation. It's cooperative, right? Senders and receivers is a completely general compositional asynchronous framework. It doesn't know anything about the actual mechanism of concurrency that we have, like interrupts, right? So it doesn't know about threads. It doesn't know about anything like that. So it cannot cancel things, right? It cannot stop a thread. It doesn't know about any of that. So cancellation is always cooperative. And the way it works is that receivers have environments, and those environments are like dictionaries of stuff. one of the things in that dictionary potentially is a stop token that you can provide on the outside receiver with a stop source. And we can query a stop token from that receiver's environment, right? If you do nothing, you get the empty environment and you're not stoppable, right? Because the empty environment doesn't give a stop token that can be stopped, or that reports cancellation requests, I should say. But a richer environment, we can enrich the environment with things to allow this. Okay, so let's take a look at how that works. First, we need a stop source. A stop source is one of these non-movable things, because stop sources contain, again, atomics and stuff like that. So we'll put that outside. It can't live inside a receiver because receivers have to be movable, right? So we'll just put it outside somewhere. Oh, and so it's named. The type name T here is so that we can use a template as a convenient way to have different statically available but tagged objects, basically. The receiver is going to have an environment that exposes the stop token from that stop source. Okay, so here's the environment. When we call get stop token on the environment, we're going to return the stop token. We're going to get that stop token from that stop source. In making a stoppable receiver, we're going to make sure that stop source is alive when we create the receiver. And when we get an environment here, we're going to return an environment that has a token from that stop source. Okay? So this is the way we're going to orchestrate cancellation from the outside. We can have a receiver on the outside. It's inside start detached, but we can parameterize start detached, and this is kind of the way it happens. Imagine you are starting the operation, you're connecting the sender that you've made. If you connect it to a stoppable receiver, it's going to be able to reach into that receiver's environment, find that stop token, and so it's going to know by checking that stop token if you've asked for it to be cancelled.
When all also has a stop source.
When all does, and I think when any does too. Yes. Because they need to orchestrate the cancellation of their sub-senders, right? So they keep a stop source inside them, and when the external stop source gets requested, they have a stop callback, which we'll see a diagram of that in a minute. It'd be better than I can explain it to you right now. So all these in-place stop sources, stop tokens, callbacks, they're the same as the ones they have the same interface as the ones you can find on CP reference, right? We have stop sources, we have stop tokens, we have stop callbacks. The only difference is their implementation. They use intrusive lists, at least in my implementation, because stop callbacks, again, there's nowhere to allocate them otherwise. And they need to be in that list. They need to have stable addresses. This is the same as you can find on cpreference.com. We already have stop source, stop token, stop callback. There is a naming note here. Should it be in place or in underscore place? C++ is already inconsistent. I don't know. I don't mind. OK, how does cancellation work in code then? So we've got a sender. We start it, and that that happens under the hood in the consumer, but you can imagine. So it's starting. After line 8, we've kicked off the work, and it's running asynchronously. Then we're going to ask it to stop by asking the stop source to stop. That's the same stop source that the receiver knows about. The receiver has the stop token for it, and the senders can look at that stop token. OK, but how does that work for real? Because we've got the receiver on the outside that has the stop token, right? And all the rest of those internal ones are those interposing receivers from the adapters. Well, some queries, and get stop token is a query, they have this status where they can be forwarded through environments. So in the same way that we build up operation states in an onion, we end up building these environments in the onion of receivers that can look through the onion layers, right? And this is kind of how we do that. So a forwarding environment takes an environment any query that is designated a forwarding query, like get stop token, it will forward the query onto the environment that it captured. Okay, so this is the let value receiver that we saw earlier. And it has nothing special in its environment, but its environment is a forwarding environment, right, of the downstream receiver. So we get the propagation of the environments from the outside of the onion toward the inside, or if you like, from the end of the pipe chain toward the beginning. So what this means is that the upstream sender from let value can ask the receiver that it got connected to for the environment, right? And that's going to be this receiver. And this receiver is going to say, oh, my environment is just, this is just a forwarding environment of the downstream receiver's environment, right? So you can see that it got propagated up the chain. And this is how that state, that cancellation request, gets threaded into the onion from the outside. Everyone cool with that? Okay. Now, Gaspar just said some of these adapters explicitly handle cancellation because they, like when any and when all, right? They explicitly orchestrate the concurrency. They do their own cancellation because when any is a race, right? For example. And in that case, they contain their own stop source in their own operation state that hooks into the external one. This is text, but let's take a look at a diagram. Okay, so here we've got a when any, and it's the inside operation state there, and it's wrapped with some outside things. We've got a receiver on the outside, and the receiver on the outside has a stop token in its environment. That's this little blob. Inside the when any operation state, we've got our own stop source, which for each of our subsenders, their receiver environments have stop tokens for our stop source. Okay? And we have a stop callback that will be called when the external stop token, because we can ask the receiver that got passed in its environment, and it has a stop token, and we can hook into that with our own stop callback. Right? So when this guy gets asked to stop, we'll get a callback, we'll stop our own stuff. So if we normally complete, this one wins, and when this one wins, we call cancel. We call cancel on the other receivers, which means calling request stop on our stop source. And then the other receivers, or the other running operation states, have the opportunity to say, is stop requested on their receiver's environment stop token, right?
Or have their own stop callbacks.
Or they could link into their own stop callbacks. Exactly. So then they get cancelled, they finish, and we finish with set value, right? The other way we might, David.
You said you requested cancellation, but they could ignore that request and complete normally.
Yes.
Cancellation is always cooperative.
Okay.
If we cancel from the outside here, what we're going to see is these guys are running. When we requested cancellation here, our stop callback was called because we registered it with the outside stop token. And our stop callback cancels our stop source, and that results in canceling all of our subsenders.
If it was built from the inside out, why doesn't that tuple receiver for the stop callback go to each of the individual ones in the?
Why doesn't this reflect into these?
Yeah.
Why aren't these the same as this?
Because when
they need them.
The audience is asking
processing, it needs to trigger cancellation on its own.
It needs.
The receiver has a switch.
Okay, so we're getting close to the end, so let's reach the end. So that's how environments work, propagating that stuff from the outside in, and it's cooperative. So let's talk about allocation. Now, I see, and you might also have seen on social media, a lot of examples like this one. This is kind of like something Eric posted. And they always use sync wait. And we see now how this is able to use no heap allocations. Like there's no heap allocations in any of these senders, and there's really no heap allocation that needs to happen here. But I never want to use sync wait. I want to use start detached or something akin to it. I never want to block. The operation state needs to live somewhere, and it's not on the heap because there is no heap. And this start detached as proposed returns void. So I don't have a handle to something I can cancel either. So there's a few changes in my implementation here. Just a note, P2300 moves fast. It still has start detached, I think, but there's a new proposal which is for async scope, which might subsume some of this behavior. But the basic idea is I'll still be able to fire off work asynchronously like start detached does, maybe with a half a dozen line async scope. Well, the memory has to live somewhere. So this is my implementation of start detached. It's going to return an optional pointer to a stop source. First thing to note. Second thing to note, it's going to be tagged with this thing. So every call site is potentially unique, tagged with a type, right? Because this stuff has to live statically, and it's a good idea. The only idea I have is to identify it by call site. We're going to ask for an allocator. Now, this is looking at the sender's environment, and it could be that I need to look at the receiver's environment, but we're gonna get an allocator from somewhere in an environment. Given that allocator, we are going to have, it's got a construct call. Now, my allocator today is not like a standard allocator. Since I was dealing with senders and receivers, it seemed weird to have the allocator return something. So instead of returning, I have it call a function because it's continuation parsing style, right? But this is just an implementation choice. Our operation state is going to be unique by the tag, and it's going to know about the allocator because when the operation state finishes, it's effectively going to call delete this. It's going to clean itself up with the allocator, right? Well, given that, all we need to do is say, let's have a stop source. We're going to return the in place one. We're going to construct a operation state, and we're going to set its stop source pointer to, the operation state is going to contain a stop source, non-movable, right? That's where it should live. But we're going to report that back to the outside, going to start it, etc. The start detached operation state, when it completes, it's going to call die, right? The receiver, when the receiver completes in any way, so set value, set error, set stop, it's going to tell the operation state to die. The operation state die is just going to, what I said, effectively delete this. It's going to tell the allocator to destroy it. The allocator driver does what you might expect. Now, there's some stuff here to do with allocation limits. It's going to get an allocator with this name and this limit. This is specializable. For the operation state, that's the T on line 4. It's going to construct the operation state, and it's going to call the function with that operation state. The allocator itself is fairly boring. It has some storage. It has what you'd expect. It does what an allocator does. It's kind of a static allocator, so it has that storage, right? And it calls construct at in the end. And we can specialize the allocation limit. So yeah, using start detached is idiomatic in embedded code. Kirk?
Because you're returning a value from start detached, I don't think you need an allocator, because you can return an object that contains the operation state and calls start on it in its constructor and has the stop source interface. So you get all the functions you have in the allocation.
Okay, possibly. Yeah, I could do that. Okay. I'm at time, so we're very close to finishing. The point here is that we can deal with allocation, right? Even in embedded. None of the machinery you've seen imposes any extra allocation, right? So we only need to deal with locating that operation state, and that's it. And of course, we have the regular embedded engineering problems of using care over reentrancy and such. We deal with those in the normal way. So I have run out of time at this point. I would like to just share some closing thoughts. Thank you for sticking with me. I know it was a lot of code. I hope that this talk has given you a good dose of understanding better by implementing. The design is the important part here. The implementation almost is secondary, but the design is very composable. And the real strength of this model is not in scaling up. In a sense, the strength of any asynchronous model is not that we can run it on hundreds of cores and loads of hardware. But the real power is that we can actually scale it down. Like this works the same way if you just run on a single thread and all of your schedulers are in line. And it's just as efficient as calling functions in that case, right? That's the strength of the senders and receivers design. And they are totally reasonable, implementable, and fun in the embedded space. Thank you very much.